So the Fire Centre Research Hub is striving to break down barriers between disciplines and between the university and agencies. Part of that is that where our seminar program, it's not a series, is a certain degree pop-up, and it pops up at different locations, because one of the things that we notice, maybe it doesn't work, maybe the people are reading download, but we would like to have more practitioners, so we're willing to actually move the seminar program into town to try to capture that. Maybe the next breakthrough is we'll start having our seminar program at Tas Fire Service. And we're trying to make it in lunch times as well as afternoons, and we're mixing it up a bit, so it's still a work in progress, but seems we're settling on Tuesdays and Thursdays, lunch times and 4 o'clock. So I'd like to introduce and welcome Jason Sharples. Jason and I were able to spend a bit of time together last year at a fire conference in Portugal. And I really enjoyed his talk, and I have a student who's working on a subject matter that he's basically globally dominant in. I thought it was a tremendous opportunity to bring Jason here to really benchmark what we're doing, but also to build these linkages, because the other thing we're wanting to do with the Fire Centre is to actually build a confederation of linkages of researchers right across Australia, have better exchanges. Jason works at the University of New South Wales in Canberra at the Defence Academy, which is I've actually has a visiting appointment or month there at one point. It's a fascinating place to be. It's very quiet because everybody's in uniform and walks around briskly.
Shooting guns.
Anyway, Jason's going to be talking about Pyrocumulonimnbus, and what I thought I'd say now before I forget is he will be going in the afternoon, but we thought we'd use the advantage of being in the city and we could wander off and have an informal bite to eat afterwards if we can extend the discussions. So thank you very much, Jason.
All right, thanks David, and thanks everyone for coming. Really appreciate the opportunity to come down here and talk to you. So what I've put together is, I guess, a bit of a synopsis, a bit of a sort of coming together of some of the research we've been doing in our group at UNSW Canberra over the last, gosh, what's about, over 10 years now. What we're really interested in is looking at these large-scale fires. So, not the run-of-the-mill fire that you get quite often, but these big sort of high-impact events. Title of the talk is Linking Local Wildfire Dynamics to Pyrocumulonimbus Formation. I'm going to say pyroCb instead of Pyrocumulonimbus because it's easier to say. But really talking about what role the fire actually plays in these sorts of events in addition to other factors. So I'm going to start out by trying to give you an idea of what we mean by pyroCb, or an extreme wildfire more generally. And the way I think it's useful to do that is start out by telling you what one isn't. This is a picture of Alan MacArthur and his research group in the 1960s up on Black Mountain in Canberra doing an experimental burn. Okay, so clearly not an extreme wildfire, but I show you this just to make the point that when we think about the models that we have at hand these days to deal with fires, predicting what fires are going to do, these are the sorts of fires that they were trained on. Okay, so it's the data from these sorts of fires which underpin the current models that we're using. Still, there are plans to move to a more current model, Project Vesta, or dry eucalypt forest fire model, but still fairly small scale experimental fires are what's being dealt with as the underpinning experiments. So that's not an extreme fire. That one there, well, it might be, and certainly if you look in the media, you'll get news reports saying that that's a firestorm, using these sort of very evocative language to describe it. I mean, that could be a firestorm, it could be an extreme wildfire. The point there is we're really too close up to tell. Okay, the sort of wildfires I'm talking about as extreme wildfires are really ones that you need to take a good 20 to 50 kilometre step back and take them in to see what you're dealing with. Okay, so there's the Denali fire, which I guess most people here are familiar with. Okay, you take a good step back and you can see, okay, we're not just dealing with a fire now, we're dealing with an atmospheric event. Okay, these are coupled fire atmosphere events. Okay, I was saying to these guys earlier this morning, these fires you don't think about in terms of area of landscape burnt, you think about them in terms of cubic kilometres of atmosphere being involved. So these fires are the most significant in terms of impacts and costs, okay, by far. So again, it's just some fairly harrowing pictures there from Dunalley. And just to remind you, it's not just the material damage that these fires do, it's also the effects on society, psychological effects as well. These kids won't forget that day. Okay, so this will stick with them and have a psychological impact as well as the material one. So really they're bad all round. I could show you lots of photos like that from around Australia, but just to point out that it's not just an Australian problem, it's a global problem. Here's a picture of one of the suburbs which is impacted by the Tubbs fire, and that's what the fire did to it. Okay, so these are highly destructive events. The only other thing to say about that picture, because I think it speaks for itself, but is when I made this slide in the end of 2017, this was the most destructive wildfire. It's now the second most destructive wildfire. Okay, so the Camp Fire in 2018 superseded it in terms of destruction. So these things are happening, and they're happening quite often. One thing that distinguishes extreme wildfires is the dominant role that embers play in their propagation. Okay, so when you think about, well, you mention a fire or bushfire to a general member of the public, what usually pops up in their head is this sort of well-organised front of fire, which moves across the landscape, burnt stuff behind it, unburnt stuff ahead of it, and you can basically, the idea is you can sort of watch this thing come at you, and when it gets close enough, you say, okay, now I'm going to run away. These sorts of fires don't tend to follow that pattern. Okay, they propagate as ember storms. You can see here, this is the firestorm impacting the western edge of Canberra in the suburb of Duffy, and really there's not a lot of flame there. It's just all embers blowing in. So, I'm going to start out by just sort of saying, here's a definition, okay? So when we want to try and study these things scientifically, we basically need a point of reference, okay? So this is a definition that we published a few years ago now. Paul was a co-author on this paper, and we basically sort of planted a flag in the ground and said, all right, when we're talking about an extreme wildfire, what we're actually talking about is a fire with certain properties, so one that exhibits deep or widespread flaming, in an atmospheric environment conducive to the development of violent pyroconvection. Now, I'll go through those terms one by one, but ultimately what this means is that you have a fire event which involves coupling of the fire with the atmosphere well above the mixed layer, okay? And this coupling is able to maintain or modify the fire's behaviour. Okay, so it goes well beyond just what's happening at the surface in terms of surface weather and fuel. This thing becomes a different beast altogether. All right, so I'm just going to go through those blue words there. So violent pyroconvection, atmospheric environment, and deep flaming. So I'll start with violent pyroconvection. It's a fairly loose and evocative term, but it's actually in the fire glossary, which dates back to about 1940s in the US, okay? Before we get to violent pyroconvection, let's just make sure we understand what pyroconvection is. Pyroconvection is just the buoyant movement of fire-heated air, okay? So a fire burns, makes the air hot. That hot air is more buoyant than the air around it, so it rises, okay? Sometimes gets pushed along by the wind as well. There's a bit of sort of terminology that's being used around the fire research and fire management people. They sort of say, well, the real aim that we've got to try and address is working out when the fire becomes pyroconvective. Now, I know what they mean by that, but they're being a little bit imprecise because basically all fires are pyroconvective, right? You light a match, it's developing pyroconvection, okay? That's why I prefer the term violent pyroconvection, so you can distinguish it from a fire like that, which has a fairly benign plume going on there, but still, that's pyroconvection driving that plume. Distinguish something like that from something like that, okay? And, the word violent there really suggests itself. I mean, you can sort of see this one here. This is in the Grampians in Victoria. It's basically just a big sort of broiling mass of atmosphere and fire all mixed together. Okay, so when I'm talking about violent pyroconvection, I'm talking about this sort of scale of things. There's another example. The thing with violent pyroconvection is it has the ability to extend high into the atmosphere. Now, why that is important is because once you start getting these things extending high into the atmosphere, okay, that's a hell of a lot of air going up, which means you've got a hell of a lot of air coming in to replace it. That can give you very erratic and unpredictable winds. You set up these big sort of convection sort of circuits going on, so all the air, dry air from up above can get circulated down to the bottom, which is going to have subsequent effects on fuel moisture contents. And the big one, as I said, is you have increased potential for embers being lofted high into the air and deposited downwind. Okay, these are very sort of violent, turbulent events, and so embers become a lot more of a problem. The most extreme manifestation of a violent pyroconvective event is pyrocumulonimnbus. Okay, and if I didn't tell you that was a fire, a lot of people, I think, well, a lot of people have said, oh, I thought it was a volcanic eruption. Okay, but that's the Grampians fire. It displays all the hallmarks of a thunderstorm. Okay, you can see basically this is all smoke down here. You can see there's a level where that smoke, or the moisture in the smoke, gets converted into liquid water. So you have your nice white fluffy cumulus cloud, and then this is the anvil. Okay, that's basically where the plume is hitting the top of the troposphere. Okay, so anvil clouds are a pretty common feature of thunderstorms. So really one of the questions that I'm interested in trying to answer is, how do we get this? Like what is actually causing this to happen? Okay, the two big things that we've sort of focused on is the role of atmospheric instability and this role of deep flaming. So what's atmospheric instability? Well, if we think about the atmospheric system or any system, the concept of stability is really talking about how resistant the system is to small changes. Okay, so if you think about the atmospheric system, if you have a parcel of air sort of sitting there like this, okay, if you give it a little push, it can do a number of things. It can either, in a stable atmosphere, it can sort of just go, well, I don't want to be pushed, I just want to sit back to where I was. Okay, so the system will sort of stabilise itself. Or you can give it a push and it'll go, yep, all right, I'm off. Okay, the analogy I use is if you think about a bowl with a ball in the middle. Okay, you have the ball there, you give it a little push, the ball will sort of wobble backwards and forwards, but eventually settle back at the bottom of the bowl. Okay, that's the stable system. If you turn the bowl over and sit the ball on top, as soon as you give it a push, it's never coming back to where it started. Okay, so atmospheric stability is really the resistance of the atmosphere to vertical motion. A stable atmosphere will resist convection. Okay, so if you give it a little bit of push from convection, it's going to say, well, I don't really want to do that. I just want to sit back where I was. So it suppresses the upward motion of the plume. In the unstable atmospheric setting, you get the opposite. Okay, so any bit of convective or buoyancy from convection, you give that air parcel, it's just going to say, yep, all right, let's keep going. Okay, and of course, if you've got an atmosphere which is more conducive to that upward motion, it's going to enhance the likelihood of pyroCb development, because ultimately, for pyroCb to occur, you need to get to that level where you start to get condensation in your plume. Okay, just like an ordinary thunderstorm. So the way that we traditionally describe or quantify atmospheric stability in wildfire science is using the Haynes index, or in Australia we now use the continuous Haynes index, because the Haynes index was kind of saturating at very high values in the Australian environment. So there was some work done about a decade ago now, looking at extending that index to make it more suitable for Australian conditions. But basically all it's doing is it's looking at two levels of the atmosphere and saying, well, what's the temperature difference between those two levels, and what's the difference between dew point and temperature at a level as well. Okay, so you sort of have this stability component and a moisture component to it. But basically the idea is the bigger the index, the more unstable the atmosphere, the more conducive it is to these big fires developing. So this is a plot that we put together with some colleagues. This is Giovanni De Virgilio, working at the Climate Change Research Centre up in Sydney. What we were interested in here was looking at the distribution of C. Haynes values. Okay, so again, higher values means more unstable atmosphere, more conducive to pyroCb development. Plotted against the forest fire danger index. Okay, so the forest fire danger index is just an index which takes in surface conditions. Okay, surface wind speed, temperature, relative humidity, and a measure of basically drought, level of drought. Okay, but all surface-based. So if you think of this, this is looking at how bad our surface weather is, basically hot, dry, and windy. And this is looking at our upper atmospheric conditions and how conducive they are to things developing upwards. Okay, so the colour shading here we've got is basically just the distribution. So you can see that, you know, the most common situations are low C Haines and fairly low FDI. Okay, and then they sort of go together in this sort of diagonal pattern here. The dots and various triangles and squares and so on we've got there, the red ones correspond to standard wildfires. Okay, so fires which didn't produce pyrocumulonimbus. The white ones correspond to fires which did produce pyrocumulonimbus. Okay, and if you have a look there, if you draw a line about there, you don't get any pyrocumulonimbus below that line. Okay, so it's saying that one of the necessary conditions for pyrocumulonimbus or pyroCb to form is you need a Haines index above a certain level, roughly about 8. Okay, and that's interesting because before we got the continuous Haines index, the Haines index stopped at 6. So we weren't able to discriminate those events at all. Okay, but it says we need a certain level of atmospheric instability for these events to occur. The other thing this graph tells us, if you look at the distribution of these white events, you've basically got white events occurring everywhere from an FDI of about 15 all the way up to 150. Okay, so it's telling us that looking at surface conditions through the FFDI is not a very good way of discriminating conditions conducive to pyroCb formation. Okay. The other things going on in this plot is you've got different shapes, triangles, crosses, diamonds, and so on. They're relating to the topographic class or the terrain class that the fires are occurring in. And if you look at most of these pyroCbs, they're either squares or crosses or triangles, which means you've got either rolling hills or steep mountainous terrain. Okay, so these things aren't tending to happen on flat paddocks. Okay, the other thing going on is the colour of the outline, and that's green for forests or black for basically grasslands. Okay, so again, all of these pyroCbs are green. Okay, there's a couple of exceptions there, but these things are predominantly happening in forests, rugged terrain, and with C Haines above about 8. So atmospheric conditions, atmospheric instability is important, but also important is the setting of the fire, okay, fuel and topography. And that's interesting to me because it brings us to the next thing we want to consider, and that's this idea of deep flaming. Now, I've got a really dodgy PowerPoint thing that I've sort of mocked up here, but hopefully it gets the point across. So as I was saying before, when we think about an ordinary fire, we're thinking of it as progressing as a front, okay? So here we've got our flames, or our flaming zone. We've got the black burnt stuff behind it and the green unburnt stuff ahead of it, okay? And this is how most fires behave, okay? 99% of fires will be doing this. The ones I'm interested, when you look at their flaming patterns, it's not so much like that, it's more like this, okay? So you get big aerial fire propagation, okay? Large areas of land which are being involved in fire quasi-simultaneously, okay, or over a very short amount of time. A lot of spotting going on. These spot fires then coalesce with each other and you get a whole lot of fire, okay, over an area. Okay, so this is what I mean when I'm talking about deep flaming. Okay, it's flames, or fires that have large flame depths, apparently. It gets confusing when you're talking to atmospheric scientists because they think of depth like that. Fire behaviourists, depth is that way. Okay, so this is deep flaming in the spatial sense, not the vertical. So that was my dodgy PowerPoint art. This is a real one from a line scan of the Wildfire in 2013, okay, up near Coonabarabran. And so you can sort of see here, right, you've got very different level of activity going on with this part of the fire here. Lots of bright orange, active flaming, lots of spots. And you compare that to these bits of the fire over here where you've just got ordinary sort of normal frontal fire propagation, okay? A thin orange yellow zone there of the front, and everything else is smouldering behind it, okay, here as well. And here having a bit of a run, but mostly if you've got this well-defined front. Here you can't really define a front very well, okay? It's just this, you know, pseudo-front, is the word they use. So basically what you end up with is just a lot of heat coming from a large area. So what produces deep flaming? Well, we're still working on this, but this is the current sort of rogues gallery. Possible triggers which give you deep flaming are strong winds, a wind change. Okay, so strong winds means that you've basically got your fire front propagating faster than the burnout zone can keep up with it, so you get a broadening of the fire front. A wind change is when you sort of have a fire which makes a long sort of front with some flanks on it. The wind change then turns those flanks into a head fire, which then spreads very rapidly. Fire eruption I'll talk about. Vorticity-driven lateral spread's got the star because I reckon this is by far the most efficient mechanism for creating deep flaming, and I'll talk about that. New one we've added to the list is overzealous use of incendiaries, or perhaps ill-informed use of incendiaries. So people sort of introducing fire in a misinformed way, putting too much fire in over a short amount of time, and mass spotting and spot fire coalescence, which relates back to these other ones as well. The point I want to make, though, is that those last four on the list involve dynamic fire propagation. Okay, so when I showed that first picture of MacArthur doing his experiments, and I said, there were these little fires, and they were basically using those to underpin a fire model. One of the assumptions they made in using that fire model, or in developing that fire model, was that when they observed the rate of spread of these experimental fires, they assumed that it would be possible to relate that rate of spread uniquely to the environmental conditions around it. Okay, so basically the assumption was that if you know what the temperature is, humidity, wind speed, drought factor, once you knew all those things, then you knew the rate of spread. Those environmental conditions uniquely define the rate of spread. And there's an assumption there which says that the fire has actually progressed to a quasi-equilibrium state. Okay, so it's sort of developed to a state, as long as the environmental conditions don't change, then the rate of spread won't change either. Now again, that's a very good assumption to make in probably 95% of cases, but now there's a whole lot of documentation around events which involve these sorts of things where that assumption goes out the window. Okay, so you can have constant environmental conditions, but have situations where your fire is behaving in anything but a quasi-equilibrium way. All right, so let's talk about why that is. Oh yes, that's the other point I made, that currently there's really no operational capacity to deal with these sorts of fire behaviours. We're working on some methods. All right, so this is two computer simulations of fires burning on slopes. Okay, when I say fires, they're not really fires. The little black bars there are just creating a heat flux. Okay, so we're just looking at the behaviour of a hot plume. Okay, which is the red you can see there. So clearly, one of the fires there is creating a plume which is lifting up and sort of moving up to the top of that panel there, whereas this one, the plume is moving straight along the surface there. Anyone hazard a guess to what the difference between those two scenarios are? It's hard to see, right? The difference is the inclination. Okay, so the one where the plume is lifting off, the hill is inclined at 24 degrees. The one where it's attached, the hill is inclined at 26 degrees. Okay. You can't even really sort of see that just looking at it, right? I mean, it's 2 degrees difference isn't a great amount. You can probably see it now that I've told you. But that 2 degree difference in inclination completely changes the behaviour of the fire. Okay? So what happened as we've gone from 24 degrees to 26 degrees is we've crossed a dynamic threshold. Okay, and there's a whole lot of complicated hydrodynamic reasons why this occurs. But basically, below about 25 degrees, your plume is quite happy to rise up to the surface. As soon as you go above that threshold, it wants to stick. Okay, now the implications of that is that here you've got a plume lifting off, so all the fuel ahead of the fire is really going to be predominantly heated by radiative heating. Okay, this situation here, the plume is actually bathing the fuel in hot gas. Okay, so here you've got an extreme convective manner of heat transfer. much more efficient, and so this is going to basically roar up that hill. Not sure how well that's come out on the screen. This is a photo that my colleague Rick McRae took when he was deployed to Canada. What the photo shows is you've got basically fire which started down the bottom here, and I don't know if you can sort of see there, you've got trees which have bits of brown on them, but most of them are still green, so a reasonably low intensity fire there. But then you've got these runs that the fire has taken up the hill. I think you can just sort of see that these runs are following these gullies, and the trees in those gullies are absolutely scorched. Okay, so high intensity runs up those gullies. Okay, the slopes are inclined at 28 degrees, which is above that 26-degree threshold. The real consequence, though, is when you look at what's happening at the top of the hill, and you've got these large regions where the crown of the canopy of the trees have been totally consumed over a fairly wide area. Okay, so again, you've got the fire roaring up here with high intensity, basically shooting embers and heat into this bit of the forest, which then goes up in, I would say, very quick succession. Okay, so you've got that deep flaming element occurring at the top of that hill there. All right, so vorticity-driven lateral spread, something I've been working on for 13 years now, but this picture is a picture I've been showing for about 13 years. I think it illustrates the point pretty well. This is a picture from the Canberra fire, and the interesting thing about it is, despite the fact that the winds are from the west-northwest, you have these occasions, and there was about 18 occasions in total during those fires, where the fire sort of made these lateral progressions. Okay, so despite the wind normally would push the fire downwind, you had these bits where the fire actually wanted to go directly across the wind. The analysis we did on these sorts of fires showed that there was a whole bunch of environmental conditions which were necessary for this to occur. Okay, so it was only occurring when you were on a leeward slope, okay, so a slope facing away from the wind. It only occurred when you're on a leeward slope steeper than about 25 degrees. Okay, so steep leeward slopes. The aspect had to be right, so it had to line up with the wind the right way. Okay, if it was too skew-if with the wind, then it didn't happen. It needed to sort of be hitting the slope at a fairly flush angle. You needed winds above about 20 kilometres per hour, and the low fuel moisture content isn't so much a condition necessary for the lateral spread to occur, but it is a condition that you need for this downwind infill of the fire. Okay, so basically the fire wants to go across, but then as it's going across, it's generating embers which are being blown downwind. Okay, and if the fuel moisture is low enough, all of those embers are going to be viable and start fires downwind, which is where you get this big yellow blob of active flame, which again is another example of deep flaming. Okay, there's a 500 metre scale bar there to give you an idea of, it's probably a 10 or so hectares going on there. I'm going to tempt the IT gods here and see if I can get this video to work. That's not a good sign. All right, so what we would have seen then is basically you've got these big fans. These are experiments we did in Portugal about 2010. You had these big fans which are pushing air straight out at you. Okay, the thing you can see there with the straw on it is basically the leeward side of a triangular hill. Okay, so the wind's pushing across that way. You've got your straw here. And Ricardo would have lit a fire and you would have seen it basically spread up the slope, but then go across in a very narrow finger of flame. As it was doing that, you would have also seen spot fires dropping down. Okay, I'll show you a picture later on. But basically the point I wanted to try to make with that was that you would have seen this very narrow finger of flame going across, just like you saw in that previous line scan, and just like you see in that one there from a different fire. This is the Aberfeldy fire in Victoria. Okay, the fire was ignited at about that point there. The wind was from the northwest, but what happened as the fire developed was it took all these lateral excursions. Okay, each of those lateral excursions corresponds with a leeward slope. Okay, so you can see there's little sort of fingers of flame moving across. Okay, we eventually got one down here where the fuel moisture content was low enough and the thing spotted enough to then cause this deep flaming event down here. Okay, so that's what the video would have showed. Okay, the ignition was about here, it goes up, but then it goes across when it hits that ridge. So we wondered about this, what was causing this for a long time. Unfortunately, you can't go out and do experiments in the landscape and this sort of stuff, okay, without probably burning down a town or something. So the only result we really had was to look to computer simulations. Okay, so you can see there on the right, we've got a little animation of a fire. Okay, the wind's coming across this way. This is a lee slope. Fire starts down here. You can see it burns up, but when it gets to the top of the ridge, you get this lateral expansion happening. The figure above that is the same thing, but it's showing you what the wind is doing. Okay, now this is wind, and the type of model we're using here is a coupled model, so it basically accounts for the effect of the wind on the fire, but also the effect of the fire on the wind. Okay, you can turn the coupling on or off. If you turn the coupling off, this doesn't happen. Okay, if you turn the coupling on, then it definitely happens, and what you basically get is as the wind is going over the top of the ridge, it's separating and recurving back. Okay, once you stick a fire under that, it stands those up, and you get this double sort of counter-rotating vortex, which then are able to move the fire sideways. So that's kind of the physics of it. And that's the reason we call it vorticity-driven lateral spread, because it's this pyrogenic vorticity which is driving it. Overzealous or ill-informed use of incendiaries. This one I like because it actually shows ill-informed use of incendiaries coupled with a VLS or vorticity-driven lateral spread event. So what we have here is a fire which is burning down towards the south coast of New South Wales, September last year. The main fire's over here, but then you have this sort of strange fire occurring here, and you wonder what it is until you look at a map and realise that there's a fire trail basically running straight along where that is. So it's almost a dead certainty that somebody's tried to put in a backburn here. I'm not exactly sure of the reason, but they were probably expecting the fire to go that way and meet up with this fire in some way. Unfortunately, what's happened is that despite the fact that the wind was from the northwest again, the fire has ignited here and has actually gone against the wind, okay, spreading up this hill. So that's at 1:20 in the afternoon. Here's the situation about 50 minutes later. So there's the original little fire that was in that last scan, and you can see what's happened is it's gone up the slope. And I'll just go back to that one, so you can see there's a ridge line there which aligns with the wind, and another one there, and you can see the fire's basically picked out those two ridge lines and gone across them, okay, in a sort of a cascade of VLS events. As it's gone across, spotting's happened, the fire's then spilled out downwind. You can see it's a complete mess, and just to add scale to it, that's about 4 kilometres spotting distance there. So that's gone up, well, that's about 50 minutes later, but I'd say most of that would have occurred in much less than 50 minutes. So within the order of half an hour to 50 minutes, you've got about 300 to 400 hectares on fire, quasi-simultaneously. That's a picture of the plume. And you can see that the interesting thing again, when you think about a fire, you expect most of the most intense activity of the fire to be at the head, the front of the fire. All the intensity here is being driven from the back of the fire, or the heel of the fire there. And there's the scan showing you the red circle there and the red circle there. These blue bits that I've added on this map are basically just picking out the slopes which are sufficiently steep and lee facing, those conditions that I said were necessary. So this gives us a good confirmation that yes, it is this VLS phenomenon which is going on here. All right. So one of the things we've been working on recently, and this is part of a bushfire natural hazards CRC project, the Spotfire project, which is being conducted in collaboration with James Hilton and Andrew Sullivan from CSIRO and Data 61. But what we're really looking at is how do we go beyond the limitation we have where we have to deal with these quasi-steady models, okay? how do we actually start to build dynamic effects into our modelling capability? Those models I showed you before, which we were using to model vorticity-driven lateral spread, they're fully coupled models, okay? Very, very computationally intensive, very complex, and if you're looking at running a simulation which lasts for about 2 hours of fire time, you're looking at about 12 to 16 hours on a supercomputer, okay? The point there is that these models are not operationally feasible, okay? You can't sit there, wait for 16 hours to find out what's going to happen to a fire which is going to be in your doorstep in 2 hours. So what we've been trying to do in this project is start to look at some of the important dynamic effects and figure out a way that we can parameterize them or reduce them in some way so that we can include them in operational models. Okay, and the real thing that we've been interested in is trying to understand pyroconvection and how it causes interactions which make fires do strange things. So this fire here is the Mount Bolton fire, 2016 in Victoria. It's a spot fire which is merging with the main fire or perhaps another fire. It's just, you can see they're just touching there. But there's a few interesting things going on. The first thing is when you look at that spot fire itself, all the flames are leaning inwards. Okay, so you've got this air pushing the fire in on itself. Okay, that makes sense because if things get hot, the air wants to go up, you have to suck air in to replace it. If you've got a nice round thing, then that air is going to come in a fairly radially symmetric way. The other interesting thing going on is you have these two instances of what we call junction fires. Okay, 2 points where fire lines are meeting at some oblique angle and creating a V. Now these sorts of fires have been fairly intensively studied over the last few years. Here's an experiment some of my Portuguese colleagues were doing back in 2012, and you can see they've just got one of these junction fires burning. Okay, these arms are about 6 metres long, and they're lighting the fire and just seeing what happens. And the interesting thing is this point of intersection basically rushes ahead at a much higher rate than what it should, you know, if things weren't interacting with each other. Again, some more dodgy PowerPoint art. You light your fire, you basically get this intensification of heat going on in that region there, which causes that junction point to rush ahead. Okay, now there's a lot of sort of navel gazing about what was causing this. Initially it was thought that because you had a bit of your fuel which is in close proximity to 2 fire lines, you were basically getting double the radiation. That was making it hotter and making it burn quicker. What we've found is actually radiation doesn't have a lot to do with it. The fact that is when you make that geometry, you create a weird geometric effect on your indraft. Okay, so instead of the indraft coming in constantly everywhere, it really gets focused on that point. Okay, we've got models which can do that now. The upshot of all that, though, is we can start to think about what effect do these dynamic effects have on the overall heat released by a fire. What I've got in these plots, okay, the first row here is one set of simulations, and the second row here is a different set. The difference between these two sets of simulations is that, okay, they both just have a number of spot fires which are being ignited. The ones on the top, though, have this pyroconvective interaction turned on, okay? So basically in the top row, the fires know about each other, okay? They're interacting with each other. In the bottom one, the fires don't know about each other, the interaction's turned off, so they're just evolving completely independently of one another. And you can see what's happening here, the colour scale here, red is more intense, and you can see when you've turned this coupling on, okay, the interaction is working. Not only do these fires get drawn into each other and merge a lot quicker, they do it with these sort of localised enhancements in the rate of spread and intensity everywhere. So one thing I always wondered about from the start of this project was, yes, you'll get all these little local enhancements, but will they add up to enough to give you a significant amount or significantly more power than what you would get if you didn't have that coupling turned on? Okay, so because we've got a model, we can do that. We just go across all the little bits of intensity there and add them all up. We do the same here, and we can basically produce graphs like this. So what we're looking at here is just the total amount of energy coming up as time evolves. Okay, so the total amount of power coming from these fires. The 4 different panels here correspond to a different number of spot fires. Okay, so this first panel here, we're only looking at 5 spot fires. Okay, this one we've got 25 spots, 50 and 100. So the interesting thing is that when you've got 5 spot fires, this interaction between the individual fires doesn't really produce any difference. Okay, it doesn't matter. Once you start adding in more fires, starting to get towards something which you'd classify as a mass spotting event, then this dynamic effect starts to kick in. Okay, with 100 spot fires, you're getting 75% higher peak firepower. Okay, so that's 75% more energy going to the atmosphere at that particular point in time. Why is that important? Why is all this deep flaming stuff important? Well, this is just some results that my postdoc, Rachel Badland, has been doing very recently. So this is all her work, not mine. But what she's done here is she said, let's just look at heat fluxes configured in different sort of spatial patterns. Okay, so the one on the left there, she's got a circular fire with 1 kilometre radius. Okay, and when I say fire, it's just a source of heat. Okay, hot. She said, okay, take exactly the same amount of heat, but instead of distributing it as a circle, let's distribute it as a rectangle with a 4:1 ratio. That's the middle panel. Then let's smear that heat out even further into a 64:1 ratio rectangle. That's the one on the right. Okay, so all these fires have the same total power, but you can see the effect that the different spatial configurations have. Okay, the colour here is basically how hot the plume is. So you can see with this big chunky circle, which is more akin to a deep flaming event, you have the plume punching well above the tropopause there. Okay, so this would definitely be a pyroCb. It's hotter for higher. As we start to thin it out, the plume's not getting as high. This one here is probably not even going to make a thunderstorm. Okay, so this is more like your ordinary fire front that you'd get. This is your deep flaming event. Okay, so this suggests why deep flaming is important. The reason we think this is happening, we have pretty good evidence on this now, is that when you have a big chunky plume like this, it's only getting mixed out on the edges. Okay, the stuff in the middle is sort of isolated, so it's allowed to sort of rise before it gets mixed out. If you've got a very thin plume or very thin fire, the plume is like this thin sheet, which is easily teased apart by the atmosphere. Okay, and you get that neutral buoyancy sooner. So this is just looking at it a little bit more detail, looking at the effect of wind in particular. So the results I just showed you were for zero wind. So that was that guy there, that guy there, and that guy there. Okay, there's a few in between there, but you can see essentially as you thin your fire out, the maximum plume height drops. As you add wind, we can see what happens. There's a 7 km/h wind, looks pretty much the same. 14 km/h wind, same sort of relationship between plume height and skinniness of your fire. And as we start to increase the wind, still at 22 km/h, which is a wind strong enough for things like VLS, vorticity-driven lateral spread, to be kicking in. You still have that same sort of relationship. 29, once we get to 36 kilometres, you can start to see these ones here are still punching a bit higher, but once we start to get a rectangle over about 4:1 ratio, the plume height's about the same. So what's happening here is the fire is starting to become wind-dominated as opposed to plume-dominated. But all those fires have the same power. Okay? It's really how you're spatially configuring that power has a huge effect on how high the plume can rise. And of course that has an implication for whether it's likely to cause a pyroCb or not. All right, just quickly take you through this as I'm running out of time. This is a fire that we looked at from 2006, the Gross Valley Fire, which produced a series of pyroCb events. What I'm going to show you is basically different stages of the progression of the fire. So we've got isochrones here, sort of at different times. So I'll start with the one corresponding to about noon. So what we have here is basically an incised valley. This is the Gross Valley. These are all sort of cliff faces along here, and all forest. I guess most people are familiar with the Blue Mountains. So this was the fire situation, the fire perimeter at about 12 o'clock. Here it is about 2 and a bit hours later, 2:40 p.m. And you can see you've got these sort of areas of almost constant signature in your line scans, so sort of quasi-simultaneous fire behaviour, large areas. This one here corresponds to a lateral expansion of the fire through a number of small-scale VLS events, and this one was basically a mass spotting event down the valley. But what you can see, as I've shaded here, is basically we looked at the radar and said, let's look at all the radar returns above a certain intensity. Okay, so the really strong radar returns. And so you've got this spatial link between where you're getting these really strong radar returns and where these sort of deep flaming events are happening. If you look at the next stage of the fire, a couple of hours later, okay, we're going to look at this bit now. Okay, we're sort of sitting there. Goes out to here, again, spreading laterally across the wind, filling in downwind with spots, and now the highest level of convection is associated with this part of the fire. So we've got this spatial link between where the really strong convective activity is happening with these deep flaming events, and we can also make a temporal connection. Okay, if we look at the echo top height, okay, so the top of the plume in the radar, you basically have these two instances where the plume hits the tropopause. One corresponds pretty nicely when this is happening, and the other one corresponds pretty nicely to when this is happening. So we've got a spatiotemporal link between maximum plume heights when the pyroCbs were happening and these sort of local wildfire dynamics going on the ground. And that's what the pitch, that's what the plume looked like from one of those pyroCbs. Can't remember which one. The other interesting thing in this fire was the role of what I call critical fire weather. Okay, so what we've got here is just a weather trace. So temperature is red, dew point is blue. They're the two interesting ones. What we can see here is as the wind switches direction to more of a westerly direction, you have a drop in dew point and a simultaneous increase in temperature. Okay, so this is drier air and warmer air. Now that's not unusual. What is unusual is the fact that this happened at 4 o'clock in the morning. Okay, so that goes against the normal diurnal cycle completely. If you were translating that into what that means for fire behaviour variables, we can look at the fuel moisture, we can look at the forest fire danger index. You can see that there's a big jump in the forest fire danger index up to sort of, well, very high to severe levels probably now. And the fuel moisture, this is the fuel moisture index, which is kind of a dimensionless measure, but the point is it drops below 5, which corresponds to an actual fuel moisture content of about 5%. Okay? Once you get fuel moisture contents below about 5%, that means your fuels are highly conducive to viable spotting going on. So what this is doing is this sort of nocturnal event is really knocking down your fuel moisture content. It's disrupting the usual moistening phase that occurs at night and basically priming your landscape for that extreme fire behaviour in the next day. And yeah, so this is a thing known as a fern event. You can ask Paul about those. Okay, so just to finish off, there are a number of other potential drivers for pyroCb that have been put forward. Long fire lines have been postulated. Mid-level moisture, okay, so moisture up in the mid-levels of the atmosphere, and the existence of a threshold firepower. I just want to address those quickly one by one. I think the long fire line we can probably rule out, as this shows. When you have your fire smeared out in a long line, it's basically just getting entrained away, the plume. Mid-level moisture, we had a look at this, or rather Rachel Badland had a look at this for me. So here we've just used an atmospheric profile without any moisture in the mid-level, and here we've purposely just built in an extra level of moisture above about 700 hectopascals, which is about 3 kilometres. Okay, so about this level here. So you can see the moisture is making a difference. It's making things a whole lot more turbulent, but in terms of the actual maximum height of the plume, it doesn't seem to be affecting it too much. So at least in this case, mid-level moisture doesn't seem to be as important as other things, but we've still got a fair bit to look at along those lines. The firepower threshold, this is work coming out of the Bureau. Basically, they've sort of said you can have this fairly nice formula which tells you about things you can measure in your atmospheric profile, which will allow you to equate an equivalent firepower threshold. And once you have a fire which emits power above that threshold, it will start to form a pyroCb. Again, I think the results that we have tend to sort of shed a bit of doubt on that, because all of the fires that we've looked at have the same power. So if there was a threshold which applied universally, then all of these should be producing pyroCbs, and clearly these ones down here aren't. So the way we've been looking at it is basically saying, if you want to predict pyroCb onset, you've got to look at the condition of the fire in terms of its potential to produce deep flaming, and also the condition of the atmosphere in terms of how unstable it is. Of course, you need to have a running wildfire in a day of raised FDR, where raised is sort of still to be determined, okay? But that graph I showed you early on sort of said, well, 15, FDI 15 would be sufficient in some cases. So that concept we've kind of put into this model, which we call the blow-up fire outlook model, or BUFO. Basically, the idea is to start at point 1 and say, do we have an uncontrolled fire in an elevated fire danger environment? If we don't, then there's no problem. If we do, then we have to go and ask a whole bunch of other questions. How strong are the winds? If they're strong enough, are we dealing with a fire in rugged landscape? If we're not, then we might still be able to get a pyroCb being driven by really strong winds, so over 40 k's, or if there's a wind change. If we are in a rugged landscape, is the fuel moisture content sufficiently low where you're going to get mass spotting kicking in? Do you have a mechanism like VLS or eruptive fire behaviour to produce those levels of spotting? If all those ducks line up, then you get to this question 9 here, which is saying, is your atmospheric instability high enough to produce a pyroCb? Here I've got C Haines bigger than 10, but again, that graph probably suggests that 8 is probably a better measure. The point is, though, really all we're doing here is we're asking about, is the situation conducive to deep flaming, and is it happening in an environment conducive for plumes going up? So we've played around with this a little bit. One case I thought was particularly interesting was fires burning across New South Wales on the 11th of February 2017. There was about 80 fires going. So really, when you've got 80 fires going, it's really helpful to be able to put your finger on the one which is going to cause all the problems. So Rick ran a BUFO analysis on that day. Here's an exact extract from his email, which was to New South Wales RFS. 3:54 p.m. on the 11th. The only specific fire to mention at present is the Sir fire. It could blow up through the influence of strong winds. The influence of the sandstone rims around all the gully heads in terms of VLS is expected to be slight, but care is needed with respect to small-scale VLS. Hopefully it's extinguished today. Well, it wasn't, and that's the situation about 24 hours later. And you can see this is the Sir here forming a pyroCb. It's the only one out of the 80 that did that. So there's another, 8 fires just there in close proximity which didn't produce pyroCbs. Okay, this is the White Cedar fire. It was basically burning in grass. So it was a significant fire, but it didn't have the mechanism for deep flaming going on. So just to finish up, extreme fires and pyroCbs constitute the most dire threat to society and environment. Okay, these are the ones that really have our lunch, and these are the ones that we're least well equipped to deal with. Okay, the current suite of fire behaving modelling frameworks don't really cut it. pyroCb occurrence also appears to be increasing in frequency around the globe, which is likely a consequence of anthropogenic global warming, but the details are fairly messy. I can just show you this little histogram now, which is the Australian pyroCb count at the end of year, and you can see 2019 has already been a fairly spectacular year. Okay, it's been the most number of pyroCbs we've counted in a season. The geometry and spatial expanse of a fire's flaming zone are critical. Okay, they're just as, if not more important than the total energy release in driving extreme plume development. This deep flaming is really driven by dynamic fire behaviours. Okay, you're not going to get it in situations where your fire's obeying the rules. Okay, it's only when you get these extra dynamic effects which then produce mass spotting and things like that. And we're still working on the problem. Okay, it's a burgeoning area of research, and still lots to be done. So just want to say thanks again to University of Tasmania, Mercy and David and Jamie. Thanks for the invite. They're great hosts. My funders, ARC, Bushfire Natural Hazards CRC, the Academy of Science, my colleagues Rick, Lawrence from Emergency Services, Domingos Viegas and his team at the University of Coimbra in Portugal, and my UNSW and CSIRO colleagues as well. And thanks for your attention and interest, I hope.
We've pretty well filled up the allocated time, and I don't know whether there's demand for this lecture theatre, but we are a small group, so we can have an informal chat. But are there any, like, absolutely supercritical burning questions? I've got one comment to make.
You haven't mentioned anything about stratospheric intrusion. The pyroplume is about causing stratospheric intrusion, then drives the fire even more.
I wouldn't say that stratospheric injection drives the fire even more. It has longer term, broader scale climatic effects, which guys like Mike Fromm in Naval Research Labs are working on. But I mean, to get a fire to punch through the stratosphere is really significant. And yeah, so a lot of those simulations that I was showing did have stratospheric injection. The Gross Valley fire had a stratospheric injection event, and I'm not sure, did Dunalley make it up that high? It was 15 Ks, right? Yeah. So yeah, it's not uncommon for that to occur. I don't think it has that much of an effect on the subsequent fire behaviour, though. That's mostly within the troposphere.
So I think we'll wrap up, but what I wanted to say is just how grateful I am to Jason, and isn't it a marvellous thing to have a logical mind? Because but it's beguiling, and we can talk about it afterwards, but what really a feature of fire are the feedbacks and the interactions and the processes which make actually understanding it so complicated, and fire ecology so complicated, pyrogeography so complicated. And it's, I have envy for somebody who can look at such a complicated process and strip it down and build it back up in a very logical and coherent way. I mean, I'll certainly buy whatever you're selling, but obviously you know that it's still more complicated, but it's an amazing achievement to be able to think about these fires in such a logical way, and I'm really grateful for your talk. Thank you.
No, welcome.
All right, well, we might wrap up, and we can go and find somewhere to have a bite to eat.